When we look up at the night sky, the Milky Way looks like a quiet, frozen river of light. It appears to be a peaceful neighborhood of stars that has existed exactly this way since the dawn of time. But that sense of calm is an optical illusion created by our physical position. Because Earth is situated within a dense, dusty galactic disk, our view of the broader cosmic environment is heavily obscured, like trying to map a vast forest while standing inside a thick bank of fog. When astronomers finally managed to look past that dust, they didn't find a static system. They found massive rippling structures, vast wrinkles echoing through families of stars in the outer edges of the galaxy's halo. They also spotted something even more violent, hypervelocity stars. These are rogue suns zooming through the galactic halo so quickly they can break entirely free of the Milky Way's gravitational grip and shoot into intergalactic space. What makes these specific escapees fascinated is that they belong to the B subtype. These stars are massive, exceptionally hot, and burn through their fuel very quickly, giving them incredibly short lifespans. Because these stars haven't been alive for very long, the force that accelerated them to such extreme speeds must have occurred very recently. These fresh ripples and fleeing stars reveal a galaxy in flux, a system defined by ongoing violence rather than ancient stability. To figure out what caused this chaos, researchers turned to the European Space Agency's Gaia spacecraft. Gaia is a space observatory specifically designed to map the precise three-dimensional positions and motions of over 1 billion stars, allowing us to track exactly where these stars came from. This diagram maps the trajectory of halo wrinkles. Running these star movements backward reveals the ripples are impact tremors from the Milky Way consuming smaller dwarf galaxies. Sliding the timeline forward shows these mergers occurred billions of years later than previously thought. The Milky Way is an active predator, still rippling as it digests its most recent prey. But what about those hypervelocity stars? Their extreme speed is caused by the Hill's mechanism. This is a three-body gravitational interaction, where a binary pair of stars ventures too close to a massive black hole. The intense gravity captures one star and violently ejects the other. By tracking the exact paths of these ejected stars, astronomers can use them as forensic trajectories. They point straight back to the locations of hidden, isolated black holes scattered throughout the Milky Way's outer halo. Finding those invisible black holes is a primary goal of NASA's upcoming Nancy Grace Roman Space Telescope. Roman is equipped with specialized infrared vision designed to pierce through the thick bands of galactic dust that block traditional visible light. Roman will hunt for these dark masses using a technique called microlensing. When a hidden black hole passes in front of a distant background star, its gravity warps the fabric of spacetime, acting like a natural magnifying glass that temporarily brightens the starlight. All of these scattered black holes ultimately orbit the massive gravitational anchor at the very center of our galaxy. In 2019, the Event Horizon Telescope captured this exact shadow. The glowing asymmetrical gas ring provides direct photographic proof of the supermassive black hole. Locating both this central giant and the isolated black holes hiding in the halo is essential. Their massive, invisible weight generates the structural forces that steer our entire galaxy. Once we map those internal gravitational forces accurately, we can look outward. Doing so with this new mass and motion data forces a recalculation of the Milky Way's ultimate trajectory through the universe. Astronomers have long agreed on how our galaxy will die. We were certain that in roughly 5 billion years, the Milky Way would suffer an apocalyptic collision with our massive neighbor, the Andromeda galaxy. Highly precise measurements from Gaia have introduced disruptive new variables into that math. Specifically, we now have accurate mass and trajectory data for 2 satellite galaxies, the Large Magellanic Cloud, an irregular dwarf galaxy currently orbiting us, and the M33 galaxy, located near Andromeda. This chart models those paths. M33's extra weight bends Milky Way and Andromeda's trajectory lines closer, making a merger seem inevitable. Adding the Large Magellanic Cloud's perpendicular orbit acts as a cosmic recoil, violently yanking our galaxy's trajectory away from its path. Factoring in the margins of error from Gaia's measurements changes the math entirely. The certainty of an apocalypse has dropped to a coin toss. There is now a 50% chance that the Milky Way and Andromeda will miss each other entirely. As our telescopes clear the dust and map the chaos of our cosmic neighborhood, we realize the Milky Way story is still actively being written. Our cosmic demise is far from guaranteed.